10th standard chapter 4 circles. So circle is a collection of all points in a plane which is equidistant from a fixed point. So that equidistance is called radius and the fixed point is called center. So this definition is given in your textbook. Now I'll draw a circle. See, this is the center. See, from center, if you draw a line such that it touches the radius, touches the circumference, then this is the radius. So no matter where this line touches to the circumference, all are equidistant, all are r only. So that defines a circle. Circle is the collection of all points in a plane which are equidistant from a fixed point, and this portion, this is the length of the outer portion, is called circumference. Okay, now in a circle I'll draw 3 lines. See, this is a circle, there's another circle, and I'll draw another circle. See, I'll draw a line like this. I'll draw a line PQ. See, in the see here, PQ is not touching circle. PQ is just a line. So now consider again where PQ intersects the circle. Line PQ intersects circle at points A and B. A and B. Now PQ has got a different meaning. Here in the previous case, line PQ was just a line. It did not touch the circle. In the second case, line PQ is intersecting the circle at points B and A. So PQ is called as secant. Okay, and AB is called chord. Now I'll draw another line. So I'll draw PQ such that it intersects circle at one point, just one point. Say that point is A here. So now PQ, the line PQ assumes a different meaning. Now PQ is called as tangent. PQ is tangent. When a line touches a circle at only one point, then that line is called as tangent. Let's see what are there in the next topic. So tangent, so the definition is given here. Tangent to a circle is a line that intersects the circle at only one point. As in the last example which I told you, line PQ is called the tangent. I'll mark this as first case, this is second case, and this is the third case. So in case 1, PQ is just a line. In the second case, PQ is called as a secant, and in the third case, PQ is called a tangent. For any given circle at a point on the circumference, you can draw only one tangent. See, for example, take the circle. At this point on the tangent, you can draw only one tangent. Now consider another example. Here at this point we can draw only one tangent. Now what is a secant in a circle? See, I'll draw a secant PQ and let let it intersect the circle at AB. Now I'll shift I'll keep point A there itself, and I'll shift the line towards left, and I'll draw another line. So let it be A. Let PQ now make A and B dash as the new line. Now again I'll shift this PQ further, keeping A as constant, such that one point is fixed. Now there's another point here, B double dash. So like this I keep on shifting this line, but point A will be same. At one point this B will coincide with A. So at one point of time the point B and point A will coincide, and that secant becomes a tangent. So in your textbook you can see the cursor at the end of the page. The tangent to a circle is a special case of the secant when the two end points of its corresponding chord coincide. So as I just explained now, tangent is a special case of secant when two ends of its corresponding chord coincide. There are some activities given in your textbook. Go through it. There's another activity here. Now in a circle, how many parallel lines can we draw? So like this. Or if I take a circle and if I start first line this way, and if I draw lines parallel to the first line this way, how many parallel lines can I draw? So I can draw 1 crores of parallel lines, I can draw 1 billions of parallel lines, I can draw 1 trillions of parallel lines. So I can draw infinite number of parallel lines. Infinite number of parallel lines. So what is infinite? What's the meaning of infinite? Infinite means a very large number. A very large number. So billions, trillions, all these are large numbers. Or you can say a number which is so big that it's difficult or not able to count, such a big number. Now there is another activity here in the textbook. They have given a cycle wheel. Now cycle wheel will have spokes. The spokes touches the circumference and the center this way. Now this wheel will touch the ground. Okay, see at the ground where the wheel touches the ground, if there is a spokes, you can see that the spokes will make an angle of 90 degree, and all these spokes are nothing but the radius. Now having the knowledge of tangent and radius, we'll study theorem 4.4. So theorem 4.1 says that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So what is a point of contact? See, if there is a circle and if there is a tangent to the circle, so tangent touches the circle at one point, right? So let the circle be centered at O, and let xy be the line, and let the tangent touch the circle at point P. Okay, now according to theorem 4.4, now if I join O and P, OP is the radius. Now according to theorem 4.1, OP is perpendicular to xy. That's what the theorem says. The tangent to any point of circle is perpendicular to the radius through the point of contact. First I'll write the data xy. Xy is a tangent to circle centered at O, and P is the point of contact. P is the point of contact between tangent and the circle. Okay, so according to this theorem, OP is perpendicular to xy. So mathematically I should prove it. So to prove, for proof, now I'll mark a point, mark Q on xy and join OQ. So I'll mark a point Q here on xy and I'll join OQ. Now you can see OP or OQ is greater than OP. Why? See, OP is the radius. OQ is bigger than the radius. You can observe in the figure, Q lies outside the circle. That means OQ is larger than the radius. Therefore OQ should be greater than OP. Even if you take another point, say for example, if I take QR, if I take another point on xy and join it, even now OR will be greater than OP. So you take any point on XP, all will be greater than OP, and OP will be the shortest distance of all. Therefore OP will be perpendicular to P. I'll write the explanation. This happens on any point on line xy. So take any point on line xy, join that point with O, and that line will be greater than OP, and OP is the shortest distance of the point O from line xy. OP will be the shortest of all the lines. Therefore OP will be perpendicular to xy. See, now I'll give one example. Take a line and take a point. Now you draw line from that point. You draw line which touches the line like this. You keep on drawing, but there will be one line which will be shortest of all, and that line will be perpendicular to the line. So applying the same logic here, OP will be the shortest and OP will be perpendicular. You can read the remarks here. It says by theorem above, we can also conclude that at any point on a circle there can be one and only one tangent. That is, if you take a circle and take any point on it, so say let it be A. At point A we can draw only one tangent, we can't draw two tangent, we can draw only one tangent. Or on this point B, on point B also we can draw only one tangent. And there's another remark, the line containing the radius through the point of contact is also sometimes called the normal. So normal is this one, OA or OB. This is also the radius. It's also the radius is also called as normal only with respect to tangent. Don't call a radius as normal. Only if there is a tangent, that radius will have a different name, that is called normal. Next we'll solve some problems. Exercise 4.1. First question, how many tangents can a circle have? So it can have infinite number of tangents. Infinite number of tangents. See, in a circle you can draw a tangent at this point, you can draw a tangent at this point, you can draw a tangent at this point, you can draw a tangent at this point. So you can draw 1 million tangents or 10 million tangents or 1 billion tangents. So you can draw as many tangents as you want. You can draw so many that you won't be able to count. Okay, infinite means it's a big number or a very big number that you won't be able to count also. So we can draw infinite number of tangents. Second question, a tangent to a circle intersect it on one point or a single point, you can write, no problem, no issue. Second question, second sub question, a line intersecting a circle in 2 points is called, a line intersecting a circle in 2 points is called a chord. Oh no, I think it's secant. I'll change it to secant. So if there is a circle and if I draw a straight line PQ so that it intersects the circle at point A and B, then the line PQ is called secant. Secant. Then question number sub question 3, a circle can have dashed parallel tangents at the most. It can have infinite number of parallel lines. Infinite. So in a circle, how many parallel lines you can have? So in a circle, now you can draw 2 parallel tangents like this. Now I'll draw one tangent like this, and I'll draw another tangent which is parallel to the first tangent like this. This is one pair. Similarly, I can draw another pair of tangent lines like this, which are parallel to one another. So like this. So there can be infinite pair of tangent lines on a circle. Now fourth sub question, the common point of contact to a circle and the circle is point of contact, that is point of contact, point of, if there is a circle and there is a tangent, then this point is called point of contact. This is called point of contact. Let's check the answer. So you can see circles. So first answer for first question is infinitely many. So you can write infinite or infinitely many. It's one and the same. Grammatically there is no mistake. And the second sub question, first answer is one, or you can write a single point. That's also okay. Both are grammatically correct and gives the same meaning. Second sub question answer is secant, and the third one is infinitely many or infinite. Both are one and the same. It gives the same meaning. Fourth sub question answer is point of contact. Now we'll go to next question number 3. A tangent PQ at a point P of a circle of radius 5 cm meets the line through the center O at a point Q, so that OQ is equal to 12 cm. Length PQ is, I'll draw the diagram. So there is a circle and radius is 5 cm. Tangent PQ at point P, so there is a tangent PQ and the point of contact is P and OQ. PQ is the tangent and OQ is equal to 12 cm. So what is the length of PQ is the question. So now always tangent makes an angle of 90 degree to the radius, right? So here OPQ is a right angle triangle. Therefore square of the hypotenuse is equal to sum of the square of the other two sides. Therefore OQ square is equal to OP square plus PQ square. So this is 12 square is equal to OP is equal to 5 square is plus PQ square. So this is 144. 12 square is 144 is equal to 5 5 is 25 is equal plus PQ square. Now I'll bring this 25 to the left hand side. 144 minus 25 is equal to PQ square. So this is 9, then 13, 3 minus 2 is 1 is equal to PQ square. Therefore PQ is equal to square root of 119. Exercise 4.1, question number 4. Draw a circle and two parallel lines to a given line such that one is a tangent and the other a secant to the circle. So according to the question, there is one circle and a line. So I should draw a tangent and secant to the circle which is parallel to the given line. So after drawing I should get like this. Circle and the given line will be as it is. I should draw a tangent to the circle which is parallel to the given line, and also I should draw a secant to the circle which is also parallel to the given line. So to achieve this, first I will draw a circle and a line Okay, let the line be AB, given line be AB. Now there are two set square in geometry box. One is 45 degree angle set square. That 45 degree angle set square I'll place here this way. So this is 45 set square, and another set square which is 30/60. That set square I'll place like this. Okay, this is 30/60 degree set square. See, first set square I'll place such that one edge of the set square complete exactly lies on the given line. That way I will place, and these two set square, the edges of these two set square will touch. That way I'll place both the set square. Now I'll keep the top set square fixed and move the bottom set square this way, in this direction, in horizontal direction, such that the bottom set square will come here like this. Okay, I'll move such that one edge of the set square touches the circumference. Now at this edge I'll draw one line. And I will name it as PQ. That line PQ is nothing but tangent to the given circle. Now what I'll do is I'll further move the set square, the 45 degree set square. I'll further move at this position. Now at this position I'll draw another line, and I'll name it as RS. Now RS is nothing but the secant, and which is parallel to the given line AB. So after this I'll remove the set square. Finally I'll get figure like this. This is our original line AB, and PQ will be the tangent, PQ, and RS is the secant. So all these three lines are parallel to one another. This is one of the simplest method of drawing parallel lines, and there may be other method also, but this is the simplest method. To make this video simpler, I have just explained it, but in exam you should really try practically by drawing using your geometrical instruments. Next topic is number of tangents from a point on a circle. Now consider a circle centered at O, and consider an external point P. Now how many tangents can I draw from point P? I can draw one tangent like this, and I can draw another tangent like this, say PQ and PR. So I have drawn two tangents, PQ and PR. Now can I draw any other extra tangent? No, it's not possible. So on a circle I can draw only two tangents from an external point. So now if in your textbook, if you see, there is activity. So this activity is given just to make this point clear, that from an external point we can draw only two tangents. You can read and try this activity. And next theorem is theorem 4.2. I'll go to theorem 4.2. Theorem 4.2. So as I told you just now, from an external point we can draw only two tangents to a given circle. Now I'll consider the circle centered at O and let the external point be P. Now I'll draw two tangents. So PQ and PR are the two tangents, and OQ will be the radius. Now see, according to this theorem 4.2, the length of the tangents drawn from an external point to a circle are equal. That means PQ will be equal to PR according to this theorem, and we'll prove this theorem. Now I'll write the data. P is an external point to a circle centered at O. PQ and PR are tangents to the circle. So whenever you are proving anything, whenever you are proving a theorem, first you need to write the data. Data also carries marks. Now here you can see that we need to prove that PQ is equal to PR. Now in proof, see, in triangle PQO and triangle PRO, side PO is common. So side PO is common to both the triangles, and angle Q is equal to angle R. See, any tangent makes an angle of 90 degree at the point of contact, right? So this is 90, this is 90, and OR is equal to OQ. They are radius or radii. I'll write radii. Now in these two triangles, two sides are equal and one angle is equal. Therefore these two triangles are similar. Triangles PQO and triangle PRO, according to what rule? Sorry, these two triangles are congruent. So these two are congruent according to RHS rule. That means one right angle is equal, and hypotenuse is also equal, and one side is equal. Therefore these two triangles are congruent. Therefore the remaining sides also should be equal. Therefore the remaining corresponding sides should be equal. Therefore PR will be equal to PQ. So in any two right angled triangle, see, consider these two right angled triangle. If hypotenuse is equal, if this hypotenuse is equal to this hypotenuse, and any one side is equal to the other one side of the other triangle, then these two triangles are congruent. It can also be like this: two triangles, two right angled triangle, So if hypotenuse is equal, and if suppose if this two side is equal, then also these two triangles are equal. So applying the same logic here, according to RHS rule, these two triangles are congruent. Therefore the remaining corresponding sides will be equal, also remaining corresponding angles also will be equal. We are concerned with the side only. So side PR is equal to side PQ, and that proves the theorem. There are some remarks in the textbook given. Remark number 1. Remark 1. So the theorem can also be proved using the Pythagoras theorem as follows. See PQO, in triangle PQO, Q is 90 degree. Therefore the square of the hypotenuse PO square is equal to PQ square plus QO square, or PQ square PQ square is equal to PO square minus QO square. Also my PR square, in triangle PRQ, R is a right angle triangle. Therefore here also, if you apply the Pythagoras theorem, PR square will be equal to PO square minus QO square. So these two are same, 1 and 2 are same. So using Pythagoras theorem also we can prove that PQ is equal to PR. And there is another remark. So angle OPQ is equal to OQR. Angle OPQ is equal to OPR. Why they are equal? Because triangle PQO and triangle PRO are congruent. We just now proved in the theorem itself. These two triangles are congruent. Therefore corresponding angles should be equal. Therefore OPQ, angle OPQ is equal to angle OPR, and PO side line PO is the angular bisector of angle QPR. That means line PO divides angle QPR into two equal parts. Okay, and PO is the angular bisector of angle QPR. There are some worked examples in the textbook. You can read and understand. All the explanation are self-explanatory. There won't be any problem to understand. I'll be solving only the exercise problems. Exercise 4.2, question number 1. From the point Q, the length of the tangent to a circle is 24 cm and the distance of Q from the center is 25 cm. The radius of the circle is, so there's a circle. From point Q there's a tangent and the length of the tangent is 24 cm. So 24 cm, and the point Q is at a distance of 25 cm from the center. So let this be P. What is the radius? They're asking radius of the circle. So we need to find OP. So now triangle OPQ is a right angle triangle. So therefore OQ square OQ square is equal to OP square plus PQ square. So OQ square is 25 square. 25 square is equal to OP square, we don't know, OP square plus 24 square. So 25 square minus 24 square is equal to OP square. So 25 square is 625 and 24 square is 276 is equal to OP square. 49 is equal to OP square, or OP is equal to square root of 49. OP is equal to 7. So OP is 7 centimeter. That means radius is equal to 7 centimeter. We'll check the answers. So exercise 4.2, first question answer is A, 7 centimeter. Answer is correct. Question number 2. In figure 4.11, if TP and TQ are two tangents to a circle with center O, so that angle POQ is equal to 110 degree, then angle PTQ is equal to, so circle is there and there are two tangents from point T. Tangents are PT and QT, and here angle POQ is equal to 110 degree. So we know that tangent makes an angle of 90 degree at the point of contact. So this is 98 degree and this is also 90 degree. So OQTP is a quadrilateral. Therefore, sum of all the angles will be equal to 360 degree. Angle O plus angle Q plus angle T plus angle P is equal to 360 degree. Therefore, angle O is 110 given, plus this Q is 90 degree, plus T we don't know, angle T plus P is 90 degree is equal to 360 degree. So angle T will be equal to 360 minus 90 minus 90. I'll bring all these angles to the right hand side. This one, this, and 110, the other also, minus 110. So how much? I'll get 70 degree. Angle T is equal to 70 degree. So let us check the answers. So answer is B. Answer B, 70 degree. Our answer is correct. Question number 3. If tangents PA and PB from a point P to a circle with center O are inclined to each other at an angle of 80 degree, then angle POA is equal to. So question number 3. So there is an external point P, and from external point there are two tangents PA and PB. So PA and PB are the two tangents. Now, and these two tangents make an angle of 80 degree. So they are asking to find the angle AOB. So what is this angle? So this is similar to the previous problem. OBPA is a quadrilateral. Therefore, sum of all the angle will be equal to 360 degree. Angle O plus angle B plus angle P plus angle A is equal to 360 degree. Therefore angle O is equal to 360 degree minus angle B minus angle P minus angle A. I'll bring all these three to the right hand side and this also. So 360 degree minus angle B is 80 degree, these two are 90 degree. Angle A and angle B, sorry, this is 90, angle B is 90, angle P is 80, again angle A is 90. So 360 minus 90, so how much? So I'll get 100 this is 100. So angle O is equal to 100 degree. So what's the question? They want angle POA. So POA. So POA is half angle POA is equal to half of angle O. Half of angle O. Why? Because OP bisects the angle AOB. So it's 100 by 2 is equal to 50 degree. Angle POA is 50 degree. Check the answer. So exercise 4.2, third question, answer is A. So 50 degree, our answer is correct. We'll go to next problem now. Question number 4, prove that the tangents drawn at the end of a diagram of a circle are parallel. So I'll take a circle and let A be the diameter. So diameter passes through center, right? So I'll take two parallel lines. I'll draw a tangent at point A. Okay, let PQ be the tangent at point A, and let RS be the tangent. RS be the tangent at point B. Now I should prove that these two tangents are parallel. So data, what is the data? AB is the diameter of circle centered at O. PQ is tangent at A. RS is tangent at point P. Now to prove, I should prove that PQ is parallel to RS. Now OB is the radius and RS is tangent at B. Therefore OB is perpendicular to RS. How it is perpendicular? From theorem 4.1 we learnt it. Theorem 4.1. According to theorem 4.1, the tangent at any point of a circle is perpendicular to the radius through the point of contact. Therefore OB is perpendicular to RS. Now similarly OA is the radius and PQ is tangent at A. Therefore, OA is perpendicular to PQ. That means it makes an angle of 90 degree. Now you can see that BAQ, angle BAQ is equal to 90 degree, and angle QAB, and angle ABS is equal to 90 degree. Okay, but BAQ and ABS are supplementary angle. Supplementary angles. Therefore, PQ is parallel to RS. See, if there is a parallel line and if there is an intersection, these two angles are supplementary. These two angles are supplementary. Suppose this is angle 1, this is angle 2. Supplementary means angle 1 plus angle 2. Angle 1 plus angle 2 will be equal to 180 degree. So similarly here, BAQ, angle BAQ plus angle ABS is equal to 180 degree. Therefore, PQ is parallel to RS. That completes the proof. Question number 5. Prove that the perpendicular at the point of contact to the tangent to a circle passes through the center. So suppose if there is a circle and if there is a tangent to that circle, and let us say suppose P is the point of contact. At P there is a tangent and PQ is the tangent. Let us say, suppose from the point of contact, if I draw a perpendicular line like this, perpendicular line means it makes an angle of 90 degree. So if I draw a line RS like this, perpendicular to the tangent at the point of contact P, then it passes through the center of the circle, and prove it. That's the question. So I'll write the data. PQ is tangent to circle centered at O, and RS is perpendicular to PQ. This is the given data. I should prove that. To prove, I should prove that center O or RS passes through the center of the circle O. So proof. So given that RS is perpendicular to PQ, this we already know, it's in the data itself. Given data. Now PO is perpendicular to PQ according to theorem 4.1. What theorem 4.1 says? The tangent at any point of a circle is perpendicular to the radius through the point of contact. So PO is the radius, therefore PO is perpendicular to PQ at the point of contact P. Since these two lines are parallel at the point of contact P, then PO should lie on RS. Since RS and PO are perpendicular to tangent PQ at the point of at the point of contact P, then PO should lie on RS. Therefore, RS passes through O, passes through the center O, and that completes the proof. Here you can notice that RS and PO can't be two separate lines. It can't be two separate lines like this. If it is two separate lines, then point of contact will be different, but here the point of contact is same. Therefore, these two lines should lie on one another. PO, this is RS. So if these two doesn't lie on one another, point of contact will be different, which is not possible. According to the question, the point of contact is same. Therefore, these two lines should lie on one another. That means PO should lie on RS, and therefore center RS passes to the center. Question number 6. The length of a tangent from a point A at a distance 5 meters from the center of a circle is 4 centimeter. So there is a circle centered at say let O, and there is a point A, and the distance of that point from the center is 5 centimeter, and from here there is a tangent drawn, and the length of the tangent is 4 centimeter. Like this, say this is B. AB is the tangent, and we should find the radius of the circle. So what is the radius of the circle we should find? So it's very simple. OAB is a right angle triangle. Therefore, OAB is a right angled triangle. Why? Always tangent makes an angle of 90 degree with the radius. Therefore, square of the hypotenuse OA square is equal to OB square plus AB square. OA square is 5 square, OB square we don't know, plus AB square is this is 4 AB. Length of the tangent is 4 centimeter. So this is 4 square. So 25 is equal to OB square plus 16. So I'll bring 16 to the left hand side. 25 minus 16 is equal to OB square. 9 is equal to OB square. Therefore OB is equal to square root of 9, or OB is equal to 3. Therefore radius is equal to 3 centimeter. Question number 7. Two concentric circles of radii 5 centimeter and 3 centimeter. Find the length of the chord of the larger circle which touches the smaller circle. There are two concentric circles. Concentric circles means circles which have common center. Now there are two concentric circles, and there is a chord for the bigger circle, and that chord touches the inner circle at one point. So two concentric circles of radii 5, find the length of the chord of the larger circle which touches the smaller circle. So let the center be O, and let the chord be AB. Now OA and OB is 5 centimeter. That is the radius of the outer circle. Now I'll draw From O, I'll draw one perpendicular to chord AB. Now I'll call this as D. Now OD is 3 centimeter. This is the radius of the inner circle. 3 centimeter. These two are 5 centimeter, 5 centimeter. What is the question? Find the length of the chord. I should find AB. What is AB? So now consider a triangle. In triangle ODB, see, in triangle ODB, angle D is equal to 90 degree. Therefore the square of the hypotenuse, according to Pythagoras theorem, OB square will be equal to OD square plus DB square. So phi square is equal to, what is OD? OD is 3 square plus BD square. BD square I don't know. BD square I'll write as it is. So this is 25 is equal to 9 plus BD square. So I'll bring this 9 this side. 25 minus 9 is equal to 16 BD square. So 16 is equal to BD square. BD is equal to square root of 16. BD is equal to 4. Now BD is equal to 4. So AD is equal to BD is equal to 4. Why AD is equal to BD? Because the perpendicular drawn from the center of the circle to the chord bisects the chord. That's why AD will be equal to BD. Therefore AB is the chord length. Therefore AB is equal to AD plus BD is equal to 4 plus 4. So AB is equal to 8 centimeter. Question number 8. A quadrilateral ABCD is drawn to circumscribe a circle. Prove that AB plus CD is equal to AD plus BC. So figure is given. So here ABCD is a quadrilateral, and it's circumscribe a circle cell, and let us say the center of the circle is O, and also you can see in the figure that the circumference touches the sides of the quadrilateral at point P, at point Q, at point R, and at point S. So from this point of contact I will draw perpendicular. Okay, so those perpendicular will automatically join the center. Okay, so draw perpendicular from point of contact, that is P, Q, R and S. Draw perpendicular from point of contact. So they all will touch point O. Why? Because of theorem 4.1. Theorem 4.1. What it says? It says the tangent at any point of a circle is perpendicular to the radius through the point of contact. So in this question, what I was supposed to prove? I was supposed to prove that AB plus CD is equal to AD plus BC. Now after drawing perpendicular from the point of contact, they all meet at the center of the circle. Now again I'll join A and O, and also BO, CO and DO. Okay, join AO, BO, CO and DO. Now what is our SO? SO is equal to PO. They are radius. So SO is equal to PO is equal to QO, which is also equal to RO. So they are all equal and they are the radius. Let us say the radius is R centimeter. Okay. Let us say the radius is R. Now what is AP square? So AP square is equal to, now APO is a right angle triangle, because PO is perpendicular. Now AP square, or AP is equal to square root of AO square minus PO square. So this is equal to AO square minus PO is R. So PO square is R square. Similarly, what is PB? PB will be equal to BO square minus PO square, which is equal to BO square minus R square. Similarly, what is BQ? BQ is equal to square root of BO square minus OQ square, QO square. So this is equal to BO square minus R square. Similarly, what is QC? QC is equal to square root of CO square minus QO square. This is equal to CO square minus R square. Similarly, RC is equal to square root of CO square minus RO square, which is equal to CO square minus R square. RD is equal to square root of DO square minus RO square. This is equal to square root of DO square minus RO is nothing but R. And next DS is equal to square root of DO square minus SO square. So this is equal to square root of DO square minus S is R, the radius. And now finally SA is equal to square root of AO square minus SO square. So AO square minus R square. Now from these two I'll get AB. Okay, from these two AB is equal to AP plus PB. So AP is square root of AO square minus R square plus PB is equal to square root of BO square minus R square. So similarly, from these two I will get BC. So BC is equal to BQ plus QC. So this is equal to square root of BO square minus R square plus CO square minus R square. Now from these two I'll get CD. CD is equal to RC plus RD. So this is equal to square root of CO square minus R square plus DO square minus R square. Now from these two I'll get AD. AD is equal to DS plus SA. So this is equal to square root of DO square minus R square plus square root of AO square minus R square. I'll mark this as 1, this as 2, and this as 3, and this as 4. Now what is 1 plus 3? 1 plus 3 gives me AB plus CD. So AB plus CD, what I am getting? So AB is square root of AO square minus R square plus square root of BO square minus R square plus CD is square root of CO square minus R square plus DO square minus R square. Now from 2 plus 4, what will I get? So 2 plus 4 is nothing but CD plus AD. CD plus AD is equal to square root of CO square plus R square, CO square minus R square plus square root of DO square minus R square plus AD is DO square minus R square plus AO square minus R square. So this equation I'll mark 5 and this I'll mark as 6. Sorry, there's a small correction here. Here it's BO square minus R square plus this is CO square minus R square. Okay, now if you see if you compare 5 and 6, okay, comparing 5 and 6, we get AB plus CD is equal to CD plus AD. See, the right hand side of equation 5 and the right hand side of equation 6 both are same only. Therefore AB plus CD is equal to CD plus AD. Question number 9. In figure 4.13, xy and x dash y dash are two parallel tangents to a circle with center O, and another tangent AB is with point of contact C intersecting xy at A and x dash y dash at B. Prove that angle AOB is equal to 90 degree. So there is a circle and x dash y dash and xy are two parallel tangents. Okay, so this is x dash y dash and this is x y. PQ, this is O, and there is another tangent AB, and the point of contact of tangent AB is C. So we should prove that angle AOB is equal to 90 degree. So given data xy parallel to x dash y dash. So OQ and OP will be the radius and PQ will be the diameter. Okay, so PQ is the diameter. Now PQ is perpendicular to xy and also PQ is perpendicular to x dash y dash. So according to theorem number 4.1, the perpendicular drawn at the point of contact to the tangent is the radius. So PO is the radius which is drawn perpendicular to xy, and OQ is the radius which is perpendicular to the tangent xy, so x dash y dash. Therefore POQ should be diameter. So this is evident from the given data itself. Now I should prove that angle AOB is equal to 90 degree. So and C is the point of contact of the tangent AB. So I'll join OC. Okay. Now in triangle OPA, and triangle OCA, since PO is the radius and XY is the tangent, angle P is equal to 90 degree. OPA is equal to, and since OC is the radius and AB is the tangent, they will be perpendicular. Therefore OPA is equal to OCA, which is equal to 90 degree. Oh sorry, this is not required. I should prove these two triangles are congruent. I'll instead check for the sides. Now OA side is common to both the triangles. So OA is the side common to both the triangles. Now OP or PO is equal to OC. These two are radius. So these two sides are equal in these two triangles. And there's one more thing. PA is equal to PC. These two are equal according to theorem 4.1. Sorry, theorem 4.2. Theorem 4.2. According to theorem 4.2, what it says? If you draw a tangent from an external point to a circle, then those two tangents will be equal. This is what theorem 4.2 says. Therefore now A is an external point to the circle, and PA and PC are the PA and AC are the tangents. Therefore these two tangents should be equal. Now therefore these two triangles are congruent. Therefore triangle OPA is congruent to triangle OCA. So if the triangles are congruent, then the corresponding angles will be equal. So now angle PAC will be equal to OCA. These are corresponding angles. So I'll say let this be equal to x. So I'll write here, this is x degree, this is also x degree. Now similarly in triangle OQB and OCB. So in these two triangles, OB is common side to both the triangles, and OQ is equal to OC, because these two are the radius. I'll write radii will be the correct term, because it's in singular we say radius, in plural we call it radii. And now one more side should be equal now, which is that side. OB is common side. QB is equal to BC. These two are tangents from external point B. So according to theorem 4.2, these two tangents should be equal. So here also I am writing tangent from external point A. So now in these two triangles are congruent. All the three sides are all the three sides of one triangle are equal to corresponding three sides of the other triangle. Therefore these two triangles should be congruent. So OQB is congruent to triangle OCB. SSS congruency rule. Here also I am writing SSS congruency rule. Okay, so since these two triangles are congruent, the corresponding angles should be equal. So OQB angle OQB is equal to OCB angle OCB. I'll call this as Y. I mean let the measure of these two angles be Y degree. So I'll mark here this is Y degree and this is also Y degree. Now since xy and x dash y dash are parallel, so angle PAB plus angle ABQ should be equal to 180 degree. These are supplementary angles. Okay, you know that if there are two parallel lines like this, and if there is an intersection like this, this angle plus this angle will be equal to 180 degree. These two are called supplementary angle. So similarly here angle PAB and ABQ are supplementary angle. Therefore sum will be equal to 180 degree. So what is PAB? Angle PAB is equal to PAO plus OAC, that is x plus x. So x plus x, see the figure. So x plus x is angle PAB plus what is ABQ? ABQ is y plus y. So y plus y. So is equal to 180 degree. So I already took PAC as x. Okay, and this as I have taken y. Okay, therefore x plus y plus y plus y plus y is equal to 180 degree. So 2x plus 2y is equal to 180 degree. Therefore 2 into x plus y is equal to 180 degree. So 2 1s are 2, 2 9s are 18. Okay, then x plus y is equal to I'll get x plus y is equal to 90. Okay. Now in triangle OAB, see angle B, sum of the three angles should be equal to 180 degree in a triangle. Therefore BOA, angle BOA plus OAB plus angle ABO should be equal to 180 degree. So BOA, it is unknown. BOA, I'll write it as it is. OAB OAB is what? OAB is X, and ABO is Y, so is equal to 180 degree. Now BOA is equal to 180 minus x plus y. I'll bring this x plus y to the right hand side. So 180. So x plus y is 90 degree. From equation 1, I'll mark this as 1 here, you can see. So BOA is, angle BOA is equal to 90 degree. 180 minus 90 is 90 degree. So angle BOA is equal to 90 degree. So this is what I was supposed to prove. Angle at point O is 90 degree. Oh, you may not be able to see at the end, but you can understand, I think. The last but one step itself says it. Angle BOA is equal to 90 degree. That completes the proof. Question number 10. Prove that the angle between two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segments joining the point of contact at the center. So there's a circle, and from an external point two tangents are drawn like this. Let the external point be P, let the center of the circle be O. So from P two tangents are drawn. Now let there be a point of contact be A and B. I am joining OA and OB. OA and OB will be radius, and radius makes an angle of 90 degree to the tangent. So this is 90 degree, this is also 90 degree. So prove that the angle between the two tangents drawn from the external point to a circle is supplementary to the angle subtended by the line segment joining the point of contact at the center. Now we should prove that angle O plus angle P is equal to 180 degree. That's the question. So I'll write the data first. Data AP and BP are tangents from point P, okay, and A and B are the points of contact respectively. So I should prove that angle AOB plus angle APB is equal to 180 degree. Supplementary angle means the sum of those two angles will be equal to 180 degree. Now OAPB is a quadrilateral. In a quadrilateral, the sum of all the angles is equal to 360 degree. So angle O plus angle A plus angle P plus angle B is equal to 360 degree. Now we know angle A is equal to 90 degree. Why it is 90 degree? Because the tangent makes an angle of 90 degree to the radius at the point of contact. Now angle P we don't know, so angle B is 90 degree, so is equal to 360 degree. So angle A and B is 90 degree from theorem 4.4. sorry 4.1. So what the theorem 4.1 says, that the tangent to any point of a circle is perpendicular to the radius through the point of contact. So perpendicular means it should make an angle of 90 degree. Therefore angle A and angle B will be equal to 90 degree. Now, so sorry, this 90. So angle O plus angle P is equal to 360. I'll bring this 90 to the right hand side. So minus 90. So this is 180 minus 360 minus 90 minus 90 is 180. So angle O plus angle P is equal to 180 degree. Then that completes the proof. Exercise 4.2, question number 11. Prove that the parallelogram circumscribing a circle is a rhombus. See how a parallelogram looks. It's like this. So in parallelogram, opposite sides are equal in length and opposite sides are parallel to one another. So here the top and bottom portion will be parallel, and the left and the right portion, right side will be parallel and equal in length. Suppose if I put a circle which touches three sides like this, of this side if I put a circle, it will be like this. But in the given question, the parallelogram is touching all the sides of the circle like this. There's a parallelogram, but it is touching all the sides. Parallelogram is inscribing this circle, means it is touching all the sides of the circle. So now I should prove that this parallelogram is a rhombus. See, in a rhombus also opposite sides are parallel to one another, and also all the sides are equal in length. This length will be this length, this length, this length, all the length will be equal. But in parallelogram it's not like this. Opposite sides are parallel and equal in length. This length will be equal to this length like this. So now it is not known that whether the given quadrilateral is a parallelogram or a rhombus. It's not known. I mean, it's known that it's a parallelogram. I should prove that it's a rhombus. So how can I prove? I can prove if I can prove that all the sides are equal in length, then the job is done. So I'll draw the figure. So we'll assume that this is just a parallelogram now. So and it's inscribing a circle. That means all the sides of the parallelogram are touching the circle at one point. So I'll name this parallelogram as A, B, C, D. So since it's already told that it's a parallelogram, opposite sides are parallel to one another. That is AB and CD is parallel and BC and AD is parallel. So if I prove that AB is equal to BC is equal to CD is equal to AD, then my job is done. Then it means that ABCD is a rhombus. I'll write the data. ABCD is a parallelogram circumscribing a circle centered at O. That means sides are touching the circumference. So let PQRS be the point of contact between the circumference and the sides. So I'll show here. This is P, this is Q, this is R, PQR, and this is S. Now I should prove that ABCD is a rhombus. So in other words, what I should prove that? I should prove that AB is equal to BC is equal to CD is equal to AD. So it's parallel, already known that in the question itself they have told it's a parallelogram. So opposite sides are parallel to one another. And if I prove that if all the sides are equal in length, then this is a rhombus. So proof. I'll join OP. So O is the center. So I'll join OP, OQ, OR and OS. So I'll join OP, OQ, OR and OS. I'll join AC and BD. AC and BD are the diagonals. I'm joining since diagonals bisect each other, they pass through the center of the circle. Okay, diagonals pass through O, because diagonals bisect each other. Now since diagonal bisect each other, AO, length of AO will be is equal to CO. Let us say it is A. I am writing here, it's AA, and BO is equal to DO. Let this length be B. Say, okay, and let radius be R units. So PO, therefore PO is equal to QO is equal to RO is equal to SO is equal to R. And write in the diagram also, this is R unit, R unit, R unit and R unit. Now you can see in the diagram PO is perpendicular to AB, and QO is perpendicular to BC, and RO is perpendicular to CD, and SO is perpendicular to AD. SO is perpendicular to AD according to theorem number 4.1. Theorem 4.1. So what the theorem 4.1 says? The angle between tangent and the radius at the point of contact is 90 degree. So this is what theorem 4.1 says. So here PO is the radius and P is the point of contact and AB is the tangent. Therefore PO is perpendicular to AB. I'll indicate the same thing in the diagram, you can check it out. These are all right angles. So in the figure there are many right angles. Now what is the length of AB? Length of AB is equal to length of AP plus length of PB. So what is the length of AP now? Now APO is a right angle triangle. So AP is equal to square root of A square minus square root of AO square minus PO square, that is A square minus R square. So plus what is length of PB? That is square root of square root of BO square. So BO is B square. Sorry, BO is B. So B square, I missed out in figure I am writing. So BO and DO is B. So B square minus R square. So I'll mark this as 1. Now similarly, what is the length of BC? BC is equal to BQ plus QC. So what is the length of BQ? Length of BQ is B square minus R square. Check the figure. What is the length of QC? QC is square root of CO square minus QO square, that is A square minus R square. I'll mark this as 2. Now what is the length of CD? CD is equal to CR plus DR. So what is the length of CR? CR is given by square root of OC square minus OR square, that is A square minus R square plus square root of, and what is DR square? DR square is DO square minus RO square. So B square minus R square. I'll mark this as equation 3. And what is the length of DA? DA is equal to DS plus SA. So length of DS is square root of B square minus R square plus length of SA. SA is square root of AO square minus SO square, that is square root of A square minus R square. Now we can observe that 1 is equal to 2 is equal to 3 is equal to 4. That means, what it means, all the sides are equal to one another. That is AB is equal to BC is equal to CD is equal to DA. So all the sides are equal in length. Therefore ABCD is a rhombus. So the figure is somewhat little bit confusing. See, parallelogram is represented this way, okay, and actually rhombus is represented this way. Wherever you see the rhombus in Google or in textbook, wherever, a rhombus will be like this. Now a rhombus is, it's inscribing a circle. So since we did not know initially that it's a rhombus, we assume that it's a parallelogram. I mean, in the question itself it was mentioned. That's why I drew the figure just like a parallelogram. Question number 12. A triangle ABC is drawn to circumscribe a circle of radius 4 cm such that the segment BD and DC into which BC is divided by a point of contact D are of lengths 8 cm and 6 cm respectively. Find the side AB and AC. So in this triangle you can see D is the point of contact of side BC to the circle, and let E and F be the point of contact of sides AB and AC. Okay, I'll write that. So given data is ABC is a triangle circumscribing circle centered at O. So CD is 6, DB is 8, and radius OD is equal to 4 cm. Now I should find find AB and AC. Length of AB and AC I should find. So I'll mark okay, mark E and F at the point of contact of sides AB and AC. Now I will join OE and FE. So the line drawn perpendicular from the point of contact to a tangent is nothing but the radius. Okay, therefore OE and OF is equal to 4 centimeter. Join OE and OF. So OE is equal to OF is equal to 4 centimeter. What is the reason? According to theorem number 4.4. Theorem 4.1. According to this theorem, if there is a tangent to a circle and at the point of contact if you draw a perpendicular, okay, that perpendicular will be the radius. Or in other words, if you draw a tangent at any point of contact, at any point on a circle, then that tangent and radius will be perpendicular to one another according to 4.1. So therefore OE is equal to OF is equal to 4 centimeter. Now you can see that CF is equal to 6 centimeter. CF will be is equal to CD. So CD is equal to CF is equal to 6 centimeter, and EB is equal to BD is equal to 8 centimeter according to theorem number 4.2. So according to theorem number 4.2, if you draw a tangent from an external point to a circle, so we can draw two tangent from an external point to a circle, and those two length will be the length of those two tangents will be equal. Therefore now C is the external point, and if I CD and CF are the tangents, therefore CD is equal to CF. Similarly B is the external point and BD and B are the tangents, so therefore they should be equal. Okay, now I will consider the length of AB as A. You can see in the figure, this length I will consider as A, and this length I will consider as B, and this length I will consider as C centimeter. A, B and C centimeter. Okay. Let AB is equal to A centimeter, BC is equal to B centimeter, and AC is equal to C centimeter. Now according to Heron's formula, area of a triangle is given by square root of S into S minus A, S minus B and S minus C, where S is the semi-perimeter. S is given by, see, A plus B plus C is sum of all the sides is the perimeter, divided by 2 will be the half of the perimeter, that means semi-perimeter. S is semi-perimeter. So now area of a triangle is given by square root of S into S minus A into S minus B into S minus C, where S is the semi-perimeter. Now I will substitute the value of S minus A, S minus B and S minus C in this formula. First I will find what is S. So for S, I'll substitute the values of A, B and C. S is equal to A. A is, we don't know the value of A, and we don't know the value of AE also. AE I'll take as X. Okay. So A is X plus B we know that it is 8 centimeter. So X plus 8. So B plus C. So B plus C is CD plus BD. CD plus BD is 6 plus 8. That is 14. Plus C of value also I don't know. But C is CF plus FA. CF we know that it is 6 centimeter. And let AF be Y. Sorry. AF also will be X. Okay. Because AF will be equal to AE according to theorem number 4.2. So now B is 6 plus X and whole divided by 2. So if I remove the bracket, how much I will get? X plus 8 plus 14 plus 6 plus X by 2. So 2x plus, this is for 14 plus 8 plus 6 is 28 by 2 will be S. So again if I take 2 common factor, x plus 14 by 2. So 2 will get cancelled. X is equal to x plus 14. So AE is equal to AF. That point also I'll add here. So AE is equal to AF is equal to X, say. According to theorem number 4.2. Now I'll mark this as equation 1. So for equation 1, if I subtract if I subtract A on both the side, so S minus A is equal to X plus 14 minus what is A? A, see the diagram. A is X plus 8. So X plus 8. So S minus A I will get as 6. So XX will get cancelled. 14 plus 14 minus 8, I will get 6 centimeter. So similarly in equation 1, if I subtract B on both the side, S minus B is equal to X plus 14 minus B is 6 plus 8 centimeter, that is 14. So plus 14 minus 14, they will get cancelled. S minus B I will get as X is equal to X. Similarly for equation 1, if I subtract minus C on both the side, so S minus C is equal to X plus 4 the right side plus 14 minus of C is X plus 6 centimeter. You can see the diagram. C is nothing but AF plus CF, that is X plus 6. So X plus 6. So S minus C I will get, S minus C is equal to the XX will get cancelled, plus 14 minus 6 is plus 8. So I will substitute the value of all these four values in this equation. So area of the area of the triangle is given by square root of S minus S I got it as X plus 14. So into S minus A I got as 6 into 6. S minus B I got as X into, and S minus C I got as 8. So it is now 6 8 is 48. So it is square root of 48x into X plus 14. I'll mark this as equation 2. Area of triangle is also given by, see here, see the figure. I'll join CO, and I'll join BO, and I'll join AO. Now there are three triangles there: triangle ACO, triangle CBO, and triangle BAO. Now the area of the triangle ACB, area of the triangle is also given by area of triangle ACO plus area of triangle BC CBO plus area of triangle BAO, area of triangle BAO. Now what is here? In all the three triangles you can observe one thing: all have the same height, that is radius 4 centimeter. So area of triangle ACO is given by half base into height. Half base, height is known. What is the height of triangle ACO? Height of triangle of ACO is the radius, that is 4 centimeter. FO is the height. So FO is radius which is perpendicular, that is the height. So 4 into base is C, plus area of triangle CBO, half base into height. Half base is height is 4, base is 6 plus 8. CB is the base. 6 plus 8 is 14. Then plus half. What is the area of triangle BAO? There BA is the base and O is the height. So height is known. Height is 4 centimeter. So and base is A. So here 2 ones are 2, 2 twos are 4, 2 ones are 2, 2 twos are 4, 2 ones are 2, 2 twos are 4. So I'll get 2C plus. So here in place of base, which is 14 centimeter, I'll retain as B only. Let it be B. I'll write this as B. Okay. So 2C plus 2B plus 2A is equal to A. That is the area. Now this I'll mark as 3. Now see, both 2 and 3 are equal, but in different formula. That's it. But both are the area of triangle ABC. So I can equate 2 and 3. I'll simplify this further. This I can write as 2 into A plus B plus C, and A plus B plus C is actually 2S. C, A plus B plus C is equal to 2S into, I'll write 2S. So this is equal to, area is equal to, I'll get 4S. So instead of this one, I'll make this as 3. From the perimeter formula, you can see half of the perimeter is given by S. S is equal to A plus B plus C by 2. Therefore, A plus B plus C is equal to 2S. That one I have substituted here. So 2 into 2S is equal to 4S I'll get. Now I will equate 2 and 3. 2 is equal to 3. Therefore, square root of 48x into x plus 14 is equal to 3 is equal to 4s. So square root of 48x into x plus 14 is equal to 4. S is x plus 14. From equation 1 you can check equation 1 from 1. So to get rid of the square root in the left hand side, I'll square both the sides. Squaring both sides. So 48x into x plus root of this one into 4x plus 14. Now I'll square both the sides like this. So now this square root symbol and this 2 will get cancelled here. In the left hand side I'll be left with 48x into x plus 14. In the right hand side, so if I'll expand this, I'll get 4 square into x plus 14 the whole square. So 4 square is 4 into 4 and this is x plus 14 into x plus 14. In the left hand side 48x into x plus 14 is left. Now you can see, you can cancel 4 1s are 4, 4 1s are 4, 4 2s are 8, again 4 1s are 4, 4 3s are 12. So here 3x into x plus 14 is there. Now this x plus 14 and x plus 14 will get cancelled, therefore I am left with 3x in the left hand side. In the right hand side I'll get x plus 14. So I'll bring this left x to the left hand side. So 3x minus x is equal to 14. So 2x is equal to 14. So x is equal to 14 by 2 or x is equal to 7. Now what is the length of AB? AB is equal to AE plus EB. So AE is x, EB we already know it is 8. So 7 plus 8, 7 7 14 plus 1 15 centimeter. Similarly, what is the length of the side AC? AC is equal to AF plus CF. So AF is x plus CF is 6 centimeter. So 7 plus 6, which is equal to 6 6 12 plus 1 13 centimeter. These are the two lengths of the sides. Question number 13. Prove that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. So this is a circle and quadrilateral. So let ABCD be the quadrilateral and let PQRS be the point of contact. PQRS be the point of contact. So I'll write the data. ABCD is a quadrilateral and ABCD is quadrilateral circumscribing circumscribing a circle centered at O. So this is the center O. P, Q, R and S are the point of contact of sides of the quadrilateral and the circumference. So I should prove that AOB, angle AOB is equal to COD. Sorry, AOD plus COD is equal to 180 degree, and also prove that BOC plus AOD is equal to 180 degree. So I'll join AO and BO. And also I'll join CO and DO. So that's the question. So here opposite sides are AB and CD are the opposite sides, and another pair of opposite sides are BC and AD. So opposite side they subtend angles at the center, right? Side AB subtends an angle of AOB, and side CD subtends an angle of COD. Their sum should be equal to 180 degree. That's the question. Prove that opposite sides of a quadrilateral circumscribing a circle subtends supplementary angles at the center of the circle. So also BC subtends an angle of BOC, and AD subtends an angle of AOD, and their sum should be equal to 180 degree. So proof. First I'll join OP, OQ, OR and OS. Join OP, OQ, OR and OS. Now you can see that OP is perpendicular to AB, and I'll join now. And OQ is perpendicular to BC, and OR is perpendicular to CD, and OS is perpendicular to AD. So why they are perpendicular? Because tangent and radius at the point of contact are always perpendicular to one another, according to theorem 4.1. Theorem 4.1. OP is the radius and AB is the tangent, so they make an angle of 90 degree. Similarly, all the radius and tangents in the figure, they are perpendicular to one another according to theorem 4.1. Now you can see that A is an external point and AP and AS are tangents. Therefore AP is equal to AS, and angle AOP is equal to AOS according to theorem number 4.1. Theorem 4.1. So according what theorem number 4.1 says, so if you draw from an external point, if you draw a tangent to a circle, two tangents like this, then those two tangents will be equal, and also the line connecting a center and the external point, they divide the angle equally. That means this angle will be equal to this angle. So this is what theorem 4.2 says. Okay, according to theorem 4.2. So applying that logic here, angle AOP will be equal to angle AOS. So let us say this is equal to A. So I'll write here, this is angle A degree, this is angle A degree. Similarly, B is an external point. B is an external point, and PB and BQ are tangents. So therefore PB is equal to BQ, and POB is equal to angle BOQ. So here also it's the same logic. According to theorem 4.2, these two angles will be equal. So let us say these two the measure of these two angles are B degree. So I'll mark here, this is B degree, and this is B degree. So similarly similarly QOC, angle QOC will be equal to COR. Let us say it is C degree. So also let angle ROD, angle ROD is equal to DOS. Let us say it is D degree. Same thing here also, applying theorem 4.2 will get these angles. I'll mark in the figure. This is angle C degree. This is D degree. This is D degree. So AA are equal, BB are equal, and CC, this angle is equal, and this is D. Okay. Now if you add all the angles, you should get 360 degree. Okay, so there I'll add all the angle: A degree plus A degree plus B degree plus B degree plus C degree plus C degree plus D degree plus D degree is equal to 360 degree. So I'll get 2A degree plus 2B degree plus 2C degree plus 2D degree is equal to 360 degree. Now I'll take two common factor: 2A degree plus B degree plus C degree plus D degree is equal to 360. Therefore A degree plus B degree plus C degree plus D degree is equal to 360 by 2. So this is equal to 180. So A degree plus B degree plus C degree plus D degree is equal to 180. I'll mark this as 1. Now you can observe in the diagram, in the figure, A plus B degree is nothing but angle AOB. So this is angle AOB, and C plus D degree is actually angle COD. So this is equal to 180. So what it means? The angle subtended by the opposite sides AB and CD, their sum is equal to 180 degree. Okay, and I'll write the equation once again: A degree plus B degree plus C degree plus D degree is equal to 180. Now consider A degree plus D degree. See, A degree plus D degree is nothing but angle AOD plus B degree plus C degree. B degree plus C degree is nothing but angle BOC is equal to 180 degree. So here opposite sides BC and AD makes an angle such that their sum of their angles is equal to 180 degree. So this I'll mark 2, 3. So 2 and 3 establishes the proof. So 2 and 3 establishes the proof. That completes this one. Summary of this chapter. Point number 1: the meaning of a tangent to a circle. So tangent to a circle is a straight line which touches the circle at only one single point on the circumference, like this, or it can be like this. Okay. A, B, P, Q are tangents which touches at single point. AB touches at point C, PQ touches at point D, this way. These are all tangents. Next point is the tangent to a circle is perpendicular to the radius through the point of contact. So always tangent is perpendicular, where it makes point of contact and perpendicular to the radius, like this. So here tangent and radius will be perpendicular to one another. This one we learnt in theorem 4.1. Okay, next, third point, the length of two tangents from an external point to a circle are equal. If there is a circle and from an external point, if we draw two tangents, okay, say external point is P, and we draw two tangent such that it touches circle at A and B, then AB will be equal to PQ. So this we learnt in theorem 4.2, and that completes this chapter.